Hello everyone. So now we are going to talk about the refraction index and how to measure it, as well as the total internal reflection. So as we know that the light or the electromagnetic waves speed is different in different mediums. So in vacuum or space or like air, it is the maximum, which is 3 multiplied by 10 to the power 8 meters per second, but this value changes in different mediums. So basically, the refraction index, it depends on the speed of the light in different mediums, and N originally is equal to C, the speed of light, over the speed in the medium itself. So here, in air, N is equal to 1 for air. Basically, this N is going to be, the refraction index is going to be equal to 1.33 in water, and basically is different for different materials. But how to measure this N, as we actually cannot do the measurement of the light speed or the speed of the light inside the medium, but we have something called Snell's law. Snell's law, which basically says that N1, the refraction index of one material, sine theta incident in this material, or theta 1 of the light or the electromagnetic waves in this medium of N1, it's equal to N2, the refraction index of the other material, sine theta 2, the angle of the light and the other material. So let's take this forward and see how would we measure the refraction index of any specific material. So let's start from here, N1 sine theta 1 equal to N2 sine theta 2. Let's say that we have two different materials. Material with N1, refraction index 1, material of refraction index 2. Okay? Then basically we say that if the light is going from the material number 1 and going perpendicular basically to the surface of this other material, the light is going to go through without any problems. Okay? And we usually call the angle here between the incident ray and basically the surface of the second material is equal to 0. So the angle here, theta here, is equal to 0, or the incident angle. And when the incident angle is equal to 0, this is going to be also the outcome, or the refracted angle is going to be 0. Okay? So the output angle is going to be also 0. However, if you start to have a different or a higher incident angle, so let's say this is the center line, we are going to have an incident or like a ray coming from this material with some angle, theta 1. So from Snell's law, it said that the refracted, the ray of light is going to be refracted inside the other material with a different angle. So basically, this is going to be here. So it's going in this direction, going there, and this is going to be theta 2. And basically, knowing N1, N2, and theta 1, we can find theta 2 using Snell's law, this one. In our case, how to do the measurement? Basically, we are going to say, okay, N1 is going to be for us acrylic, and N2 is going to be air. We know the N of air, N2 is equal to 1. So basically, we will put some light source here and we will make incident angle so that we have this one, and we will see the refracted angle. We will measure these two angles so that basically we have theta 1, theta 2, and n2 of air. Then we can find the n1 of the acrylic. So this is how to measure the refraction index in our experiment. Now there's a very interesting phenomenon that happens. If this incident angle goes up, this refracted angle is going to go up as well from this relationship. Okay, so n1 sine theta 1 equal to n2 sine theta 2. So this one, if this one is going up, this one starts to increase. Until a certain moment, this angle is going to be basically tangent here to the surface of the second material. So the angle becomes 90. So here, n1 sine theta 1 is going to be equal to n2 sine 90, which is equal to 1 basically. And in this condition, we call this angle that we start to have this 90 degrees, we call it the critical angle. Critical angle. So, sine theta critical is equal to n2 over n1. Any increase in the theta after theta in the theta incident more than theta critical, we are going to experience something called total internal reflection. So at any case that we have the theta incident is bigger than theta critical, okay, so what happens here is basically total internal reflection. So now in this case, let's say we have this one, the center line, we have the ray that's going inside. Let's say this is theta incident, and in this case theta incident is bigger than theta critical. So what happens here, we have total internal reflection. So the ray is going to go from here and it's going to go back in the same medium with the same theta incident. So it becomes theta reflected is going to equal to theta reflected is going to equal to the theta incident, because we have total internal reflection. So we are going to do this in our experiment by basically keep increasing the theta until we see that the refracted angle becomes 90 degrees, and if once we increase the incident angle by a small degree, we have total internal reflection, and by then we can calculate the critical angle for our medium. I hope you got it, and let's go to do the experiment. So this is the setup. So we have here the PASCO optics ray table. We have the optics bench. We have acrylic half cylinder lens. We have slit mask and slit plate that has many slits. The objective of having these two, it's basically to mask it and to only have one slit showing, okay, so that the light can go through it. Then we have the light source here. As an alternative, you might have like something else instead of these two. You could have a light source that already has some slits inside. For example, this one has 1 slit, 3 slits. It has also 5 slits. It has colorful, like different filters, blue, green, and red. And this is the light source. But for today, we are going to use only these two, the slit mask, slit plate, and the light source, and of course the manual. So let's do the setup and the experiment. I have changed the bench by another one, and basically I added this table holder, the holder itself, okay, for the slit plate. So first we'd like to put the light sensor on the top of the optics bench. Let's connect the power supply. So we have the light right now. And now let's put on the holder the slit plate first. Then we put the slit mask so that we show only one slit. Okay, and let's put it. Let's put the ray table on the top in the middle, and we need to put this acrylic. We need to put this acrylic lens basically here. Make sure that it's basically in the middle, maybe on this shape of the cylinder lens. And now we are going to turn off the light to see better. I need you first to make sure that you only have a thin ray of light, that this one, and basically I need you to make sure that the light ray is taking, or it is on the whole disc. Okay, then you place the lens. And basically when the lens it is in the middle, you should have in 0 degrees here. This ray should be on the 0. So 0 input, 0 output. Okay, and let's start to rotate the disc itself and see what happens. So when the disc, you get it to 10 degrees, we can see the outcome is 15 degrees. If the disc, if rotated to 20, becomes 30. I need you to take 5 measurements of 10 degrees increments. So we have 30, it becomes around 48, you have 40, it's around 74, then in 50 you can see that they had a totally different behavior. So using these points or rays before the reflection, basically up to somewhere here, up to the 70, up to 30-ish or 40-ish, we can take the measurements so that we can get the index of the acrylic or the lens that we have here. Here, after increasing the rays, or like the angle of incident, we can see that the light suddenly converted from a refracted light to a reflected light. So this angle that we see that the light is almost kind of having 90 degree of the refracted light here, we can say that this is the critical angle, which is approximately 40 degrees or 41 degrees. Okay, any incident angle above 40 or 41, we start to have the full reflection and basically total internal reflection. You can see it here. And the angle right now 60, because this is center line. Okay, and on this lens. I hope you got here the total internal reflection. I hope you liked the lab for today and you've learned something beneficial. If you liked it, please press the like button and subscribe, and wait for me for our next physics lab. Thank you.
Polarization.